Welcome to today's deep dive, where we'll be exploring a fascinating new concept in chemistry. We're going beyond the familiar rows and columns of the periodic table and diving into something called the charge matrix. It's a completely new way of looking at elements, and it might just unlock secrets about matter itself.
It's a pretty intriguing concept.
Right.
What's really fascinating about the charge matrix is that it allows us to view elements not just by their atomic number,
Yeah.
but also by their unique charge characteristics. We're talking about the interplay of these positive and negative forces within every single atom.
Okay, that does sound intriguing. But before we get too deep, maybe a little refresher would help. Can you remind me how the periodic table is traditionally organized?
Sure. So you're probably familiar with the classic layout. Elements are arranged in order of increasing atomic number, and that reflects the number of protons in the nucleus. This
Mhm.
arrangement creates those familiar rows and columns where elements with similar chemical properties are grouped together.
Right, like the alkali metals,
Mm.
those highly reactive elements in the first column, or the noble gases, those stable elements in the last column.
Exactly. The periodic table is truly a masterpiece of organization, but the charge matrix actually takes it a step further. It suggests that the overall charge of an element isn't static, but can actually shift based on things like electron shielding, ionization potential, and even some of those mind-bending quantum effects, especially in heavier elements.
So it's not just about how many protons and electrons an element has, but how those charges actually interact with each other.
Precisely. It's like looking beyond the surface, to understand the underlying forces that govern how elements bond and react and ultimately shape everything around us.
That's pretty amazing when you think about it.
Yeah.
Okay, let's unpack this charge matrix idea a little more. When we talk about the charge of an element shifting, what exactly are we talking about?
So imagine an atom with its nucleus at the center and those electrons whizzing around in those cloud-like orbitals. The charge isn't just some fixed number, it's a dynamic interplay of all these different forces. For example, those inner electrons can actually shield the outer electrons from the full pull of the nucleus. It's like they're creating this buffer, effectively reducing the overall charge that the outer electrons feel.
Oh, okay, so even though an element might have a certain number of protons, the actual charge influencing its interactions could be different because of this shielding.
Exactly. And then you have ionization potential, too, which is the energy it takes to remove an electron from an atom. Elements with low ionization potential, like the alkali metals we mentioned earlier, they tend to lose electrons easily, forming positive ions.
So in this charge matrix model, we'd see those alkali metals with a strong tendency toward a +1 charge, because it's relatively easy to strip away that outermost electron.
You got it. Now, as we move to those heavier elements, things get even more interesting because quantum mechanics starts to really play a significant role. Those electrons are moving so fast, and relativistic effects, and yes, I'm talking about those linked to Einstein's theory of relativity, start to influence their behavior and interactions.
Hold on, relativity in chemistry. I'm trying to wrap my head around that. How does that even work?
Think of it this way. As electrons in heavier atoms move faster, closer to the speed of light, their mass actually increases, and that affects how they interact with the nucleus. These relativistic effects can significantly alter both electron shielding and ionization potential, which makes those charge calculations even more complex.
So we're essentially combining quantum mechanics, electron configurations, shielding, ionization potential, and relativity to figure out the charge behavior of these super heavy elements. It sounds incredibly intricate.
It definitely is, but that's also the beauty of this charge matrix model. It really allows us to look beyond the simple periodic table and start predicting properties of elements that haven't even been discovered yet.
Okay, I'm definitely hooked. This charge matrix sounds like a treasure map to a whole new world of chemistry. But let's get specific here. How does this model actually work for predicting these new elements?
Well, remember that the periodic table itself is built on patterns, right? Elements in the same column tend to have similar chemical properties because they have the same number of valence electrons, those outer electrons that are involved in bonding. The charge matrix actually takes these patterns and elevates them, giving us a more nuanced understanding of those trends.
So by understanding the charge behavior of elements we know, we can use the charge matrix to kind of extrapolate and predict the properties of those heavier undiscovered elements, even before we've even created them in a lab.
Precisely. We're moving from passive observation to active prediction, and those predictions can be incredibly specific. For example, let's look at element 119, unanium. It's been synthesized, but it's so unstable it exists for just fractions of a second.
Wow, that's incredibly fleeting. But even with that, we can make predictions about its properties.
We can. Based on its predicted electron configuration and its position right below francium in the periodic table, the charge matrix suggests that it might behave similarly to other group 1 elements, those alkali metals.
So like sodium and potassium, those metals that react explosively with water.
Exactly. But element 119 is predicted to be even more reactive, potentially even more explosive, because of those intense relativistic effects we talked about.
Okay, so element 119, it might be this super heavy, super reactive alkali metal. That's incredible. What about element 120?
Element 120, based on its charge matrix profile, is predicted to have a strong tendency towards a +2 charge, similar to magnesium and calcium in group 2.
Those are the elements that make bones strong. So element 120 might be a super heavy bone-building element.
It's all speculation at this point, but the possibilities are fascinating. And it's not just 119 and 120. The charge matrix suggests that element 121 might even have variable oxidation states, meaning it could take on different charges depending on what it bonds with.
So element 121 could be like a chameleon of the periodic table, bonding in ways we haven't even imagined yet. This charge matrix really is mind-blowing.
And here's why this should excite you. Understanding this charge matrix allows us to see the periodic table in a whole new light. It's not just a chart on the wall anymore. It's a dynamic map to this universe of unexplored chemical possibilities. It allows us to potentially discover new materials with incredible properties.
And to potentially even design those materials, right?
Exactly. Imagine creating materials with the strength of element 120 combined with the conductivity of a super heavy metal. We're talking about a potential revolution in material science, all thanks to this concept of the charge matrix.
This is really incredible. So we've gone from rows and columns to this roadmap for discovering and potentially creating new elements and materials. But how do we even begin to grasp the complexities of this charge matrix? Where do we even start?
That's a great question, and that's what we'll be delving into in the next part of our deep dive. We'll explore the math and the calculations involved in determining these charge values, and we'll also see how those values actually translate into real-world predictions about how elements behave.
I can't wait. Stay tuned because this deep dive is only getting started.
Welcome back to our deep dive into the charge matrix. I think you've got the basic idea now that we can view elements not just by their atomic number, but by their own unique charge characteristics. Now, let's really dig into how this model actually works.
Yeah, I'm ready to get into the details. How do we calculate those charge values and how do they translate into those real-world predictions about how an element's going to behave?
It all starts with that quantum world. Remember, electrons, they aren't just these tiny balls orbiting the nucleus like planets around a star, right? They exist in this cloud of probability, described by wave functions, and those wave functions determine how electrons are actually arranged in those shells and subshells.
Okay, I vaguely remember those electron configurations from chemistry class. You know, those 1s2, 2s2 things. But how do those configurations relate to charge?
Those configurations are crucial. They tell us exactly how many electrons are in each shell and subshell. And don't forget, electrons carry that negative charge. So let's just take a simple example. Hydrogen, 1 proton and 1 electron. Its base charge, purely based on the number of protons, is +1.
Okay, that makes sense. But you mentioned before that charge isn't static. It can change based on things like electron shielding. How does that work?
Shielding comes into play when you've got multiple electron shells. Those inner electrons can partially block that positive pull of the nucleus from those outer valence electrons. It's like those inner electrons are creating a sort of a buffer, you could say, reducing the effective charge that those outer electrons actually feel.
So even though an element might have a certain number of protons, meaning a high base charge, the actual charge that's influencing its bonding, that could be lower because of the shielding effect?
Precisely. And then we've got to factor in ionization potential too. That's the energy needed to actually remove an electron. Elements with low ionization potential, like those alkali metals we've talked about, they lose those electrons pretty easily and form positive ions.
So in this charge matrix, we'd see those alkali metals with a strong tendency towards a +1 charge, right? Because it's easy to just strip that outermost electron away.
Exactly. Now, picture applying these same principles to heavier and heavier elements, and here's where things get really wild due to those relativistic
Right,
effects.
those relativistic effects. You mean like Einstein's theory of relativity?
Yeah.
I'm still trying to wrap my head around how that applies to chemistry.
It is pretty mind-bending, isn't it? But as those electrons and heavier atoms move faster and faster, closer to the speed of light, their mass actually increases, and that changes how they interact with that nucleus.
So it's not just their speed that changes, but their actual mass. That's wild.
It is. And those relativistic effects can have a huge impact on both electron shielding and ionization potential, making those charge calculations so much more complex.
So it sounds like we're combining quantum mechanics, electron configurations, shielding, ionization potential, and the relativistic effects, all to try and predict the charge behavior of these super heavy elements that haven't even been discovered yet. It's like a symphony of physics and chemistry.
It really is, and the math behind it can get pretty intense. We're talking wave function overlap and quantum corrections to account for those relativistic effects. But the amazing thing is that it lets us go beyond describing what we see on the periodic table to actually predicting what might be out there.
So we're not just passively observing those patterns anymore. We're actively using this charge matrix to hypothesize about the properties of elements that might be beyond the current limits of the periodic table.
Exactly. Think of it like a treasure map. But instead of leading to buried gold, this map guides us towards new elements, new materials, new possibilities. For example, remember element 119, an ennium that we discussed? Based on its predicted electron configuration and its spot below francium, it's very likely to have a +1 charge, just like the other alkali metals.
Right, but with those relativistic effects potentially making it behave in some really unexpected ways.
Exactly. Those effects add so much complexity and intrigue to those predictions. Then we have element 120. Its charge matrix profile points to a strong tendency towards +2, similar to magnesium and calcium in group 2.
So potentially, we're talking about a super heavy element that helps build bones. And then there's 121, which could have these variable oxidation states, meaning it could bond in so many different ways depending on the circumstances.
That's right. The charge matrix really opens up a whole new realm of possibilities. It suggests there could be elements out there with bonding behaviors that are unlike anything we've seen before.
That's incredible. We can actually use this model to not only predict properties of these undiscovered elements, but maybe even design new materials with those specific properties. Imagine creating a material as strong as element 120, but with the conductivity of some super heavy metal.
And that's where the idea of charge coherence in bonding becomes super important. Remember, it's how those charges interact that determines if a bond is covalent, ionic, or metallic.
Right. And each of those bond types gives us totally different material properties. Strength, conductivity, melting point, all of it. But how does charge coherence fit in with all of this?
Let's say you have two atoms coming together to form a bond. It's the way their charges interact, how well they mesh or cohere, shall we say, that determines what type of bond will form. If those charges interact in a really stable, coherent way, you might get a strong covalent bond, like in a diamond.
So a diamond is basically an example of strong charge coherence.
Exactly. But if that charge interaction is less stable, less coherent, you might end up with an ionic bond. That's where one atom basically steals an electron from another, creating those oppositely charged ions that then attract each other.
So different levels of this charge coherence lead to different types of bonds, and those bond types lead to different material properties.
Exactly. And by understanding how charge coherence affects that bonding at the quantum level, we can potentially manipulate those interactions to create materials with very specific desired properties.
It's like having a set of building blocks, but instead of Legos, we're working with fundamental charges and quantum interactions. And the charge matrix is giving us that blueprint to put them together in totally new ways.
That's a great analogy. Now let's push this concept even further. We've discussed covalent, ionic, and metallic bonds, but what if there are other, maybe more exotic types of bonds out there? Ones based on charge interactions that we haven't even discovered yet.
Okay, now my imagination is really running wild. What kind of exotic bonds could there be? Bonds based on magnetic interactions, or even something we just don't even understand yet?
That's what's so amazing about science, right? We don't know what we don't know. But the charge matrix provides a framework for thinking about those possibilities, a way to systematically explore all those different charge interactions and what they might be able to create.
This is mind-blowing. We've gone from simple rows and columns on the periodic table to what sounds like a revolution in material science, all because of this charge matrix idea.
And keep in mind, this is just the beginning. In the next part of our deep dive, we'll push even further. We'll talk about whether this model can not only predict new elements and bonds, but actually create them in a lab, which would open up this whole new era of scientific discovery and technological advancement.
I cannot wait. This is definitely one of those deep dives that's leaving me with way more questions than answers, but it's such a fascinating journey. Welcome back to our final part of this deep dive into the charge matrix. We've talked about the concept, the math, and even how it could predict new elements and those bonds between them. But the big question I have now is, could we actually create these elements in a lab?
That's the ultimate question, and scientists are definitely trying to figure that out. It's not easy to do, that's for sure, but this charge matrix, it does give us a kind of roadmap, a set of guidelines, you could say, for how to manipulate those charge interactions and maybe, just maybe, synthesize those super heavy elements.
So we're not just talking about looking for patterns anymore. We're talking about engineering matter, right? Like at its most fundamental level. It's almost like alchemy, but with quantum mechanics.
Yeah, that's a great way to put it. And the key here, the really challenging part, is understanding how to stabilize those super heavy nuclei. Because those elements, they're incredibly unstable. They exist for like fractions of a second before they just decay.
Right, so it's almost like you're trying to build a house of cards in a hurricane. How do you even begin to make an environment where those heavy nuclei can hold together long enough for us to even study them?
One approach that scientists have been using, and it's how we discovered elements like oganesson, element 118, is using particle accelerators. There are these massive machines that smash lighter nuclei together at incredible speeds. And the hope is they'll fuse together into those heavier elements.
But even if we manage to create those heavy nuclei, how do we keep them from instantly falling apart?
That's where our friend the charge matrix comes in again. See, by understanding those precise charge interactions happening inside the nucleus, we might, just might, be able to find ways to make it more stable. Maybe tweak that ratio of protons to neutrons very carefully, or even introduce very specific types of bonding to create a more stable configuration.
So it's not like we're just randomly smashing atoms together. We're using this charge matrix as a blueprint to guide that whole process, to give those heavy nuclei at least a chance to exist, even for a little bit.
Exactly. It's almost like this cosmic game of chess. We're strategically arranging those fundamental charges to create something entirely new.
And speaking of new, we've talked about creating new elements, but what about those new bond D types? Could the charge matrix help us engineer those exotic bonds we were kind of speculating about? Those bonds based on like magnetic interactions or maybe even forces we haven't discovered yet.
It's definitely not out of the realm of possibility. The thing to remember about the charge matrix is it's not just about the charge of a single element by itself. It's about how all of those charges interact, those intricate relationships that create those bonds.
Right. So if we could really understand those underlying principles of charge coherence and decoherence, could we maybe design materials where the bonding is something completely different than what we're used to? Not covalent, ionic, or metallic.
You got it. We might be able to make materials that have properties we've never seen before, materials that are like unbelievably strong or super conductive, or maybe even materials that exhibit these totally new, unexpected behaviors that would kind of go against everything we currently understand about physics.
Now we're talking about some really groundbreaking stuff, not just like small steps forward, but huge GE leaps. Discoveries that could completely revolutionize things like energy, medicine, computing, everything.
And it all boils down to this change in our perspective, this idea that we can understand and manipulate matter, not just at the level of the atom, but at the level of those underlying essential charge interactions.
It's kind of amazing, isn't it? That something as abstract as this charge matrix could have such huge, impactful, real-world implications.
That's the power of fundamental science, isn't it? It often starts with these like really abstract theories, but then those theories can turn into technologies that completely change the world.
It's been an incredible deep dive. It feels like we've just barely scratched the surface. There's so much potential with this charge matrix concept. It's hard to even imagine where it could lead.
That's so true. We've covered so much. Predicting and maybe even creating new elements and bonds. But what about harnessing those interactions to make energy? Quantum computing?
Yeah.
Maybe even controlling gravity?
Whoa, now you're really going for it. But that's what's so exciting, right? The charge matrix gives us a way to think big, to explore those unknowns, to see what we can do, to push the limits.
Absolutely. And that's what I hope you take away from this deep dive. What new questions are you thinking about now? What possibilities are coming to mind? Hold on to that sense of wonder, because that's what pushes science forward.
Who knows? Maybe one day, thanks to this charge matrix, we'll live in a world where that periodic table isn't just a static chart anymore, but a dynamic, always changing map to a whole universe of possibilities we can't even imagine. Thanks for joining us on this journey into the charge matrix.